So let's start by looking at building thermoplastic polymers in QuantumATK. Using the polymer building tool in QuantumATK, you can build many kinds of thermoplastic polymer systems. You can use different combinations of monomers, either as blends or as different kinds of copolymers. You can easily add in your own custom monomers to the Monomer database to create new materials. And you can also automatically select between all atom or united atom representations, which is a new feature in the S2021 version. To see how easy it is to build polymer systems in QuantumATK, let's build an example of polyacrylonitrile. First, we need to add the monomer to the monomer database, which we can do by opening the builder. So here's our monomer that we've already built for acrylonitrile. Now to make this into a monomer, first we need to add tags which shows the atom connection points. And this is where the monomers connect together to form the polymer chain. So we can do this by selecting these atoms, and in our Monomer Tags tool, just click Add Monomer Tags. And so this is add tags for the connect atoms and also for the atoms that are removed to form the polymer chain. We can now add this to the monomer database, which we do by adding from database, we go to monomers and then import. And we can now just simply drop this monomer here onto this drop zone, give it a title, and we can now add it to the monomer database. And so we can see our monomer for acrylonitrile is shown here, with also the atoms that can be removed to form the polymer chain highlighted here in pink. Now that we have our monomer defined, we can now build a polymer system. And we do this using a script that we can create using our scripter tool here. So if we open the scripter, we first need to start with a generator to create our configuration. So in this case, we use the polymer builder. When we open the polymer builder, we can see all the different options that we have for creating our polymer system. First, we need to create a polymer sequence. And here we can have multiple sequences if we're creating polymer blends or other such materials. But in this case, we'll just use the one sequence. So in the polymer sequence, we can set the number of monomers per chain and the number of chains, as well as details about the monomers. So whether we have a homopolymer, a random copolymer, or an alternating copolymer. So in the homopolymer, we can just select the monomer from our monomer database. And here we can select the acrylonitrile monomer that we defined earlier. In the polymer environment, we can either set a polymer density if we're creating just the polymer system, or we can add in a bulk configuration that can contain a surface, which we can then build a polymer surface interface. We also have the option to add in other molecules into the polymer system if we want to add in plasticizers or other kinds of additives into the polymer melt. So because we're creating a simple homopolymer, we'll just set the expected density. If we can go to the pre-equilibration step. So this is where we pack the polymer chains into the polymer system. The force capped equilibration process that we use is designed to pack the polymer chains into the melt using the minimal amount of distortion to the natural shape of the polymer chains. Finally, we have this force field tab here, which defines the force field used during the force capped equilibration. Notice here that we have some all-atom force fields, such as OPLS-AA, Dryden in the universal force field. But we also have this Dryden united atom force field as well. And if we select this, this will convert the polymer model into a united atom model and use the Dryden united atom force field on that model. So now that we've defined our polymer system, in our script we could also then add a number of other steps. So for instance, we could add in a polymer equilibration step using this polymer equilibration block. And we can also add in other steps like optimization or molecular dynamics. And here we can define different kinds of molecular dynamics. When we have our script defined, we can then run our script by sending it to the job manager, which manages running various calculations either on local hardware or on remote clusters. When the calculation is finished, we can then view the results here on the lab floor. So here we have the structure of polyacrylonitrile calculated in our simulation, and we can view this by simply dragging it across to the builder. So this is our system of polyacrylonitrile. Notice that it is a united atom model because we specified the Dryden UA force field in building the polymer. Using the United Atoms tool, we can easily convert this back to explicit hydrogen, or of course also reunite the atoms back to form a united atom model. It's also possible to build much larger systems than the one shown here. So for example, here's a much larger system that we've built using QuantumATK, which here contains 100 polymer chains, each with 100 monomers. So looking at the types of polymer systems you can build, you can obviously build homopolymers, like this model of polystyrene. You can build copolymers, such as here this terephthalic acid copolymerized with ethylene diamine. You can build blends, such as this blend here of PVC blended with PMMA. You can build branched polymers, such as this branched low-density polyethylene. You can build polymers with molecular additives, such as this model here of Kapton with boron nitride nanoparticles. You can build polymer surface interfaces, such as here this model of PMMA with a realistic amorphous silica interface. You can build crystalline amorphous interfaces, such as the example here of polyvinylidene fluoride. And you can also combine together different features to create quite complex models. So here we have a photoresist polymer with photoacid generator molecules and a quencher, all packed on a carbon surface.